So now we're starting on Chapter 8. Chapter 8 deals with counters in digital systems. Counters are super important. We can use them for lots of different kinds of functions. Not only can we count product or we can move data down a line of information, but we can also use them as frequency dividers so that we can get a different frequency out than what we put in. Here in Tinkercad right now, I've created a mod 16 counter. That means there's 16 unique outputs that this counter can generate. And I've made it using 4 JK flip-flops. The 4 JK flip-flops are tied together in a sequence. So this is a sequential logic circuit. I have all of my J and K inputs tied to high on each of my JK flip-flops, so they're all in toggle mode. And what that means is that a clock signal coming into the clock input is going to invert the output at Q and Q0 at every pulse. What that allows us to do is pass that signal down through each of the flip-flops, and so the timing of them is going to be divided by 2 every time we go down. So when I start this simulation, you'll see my counter starts to count. And my first position light here is going to blink at the frequency that I'm putting in, which is 1 Hertz. So every second, this one's going to blink. Every 2 seconds, this one will blink, because this JK flip-flop is getting its input signal from this light. This light is passing its signal to this one, so this one is going to blink every 4 seconds. This one will blink every 8 seconds. So we've divided our frequency down through here. But you also notice we're also counting. We're counting up to 15. And then resetting back to 0 again. If I had another flip-flop in line here, I could have a position out here in the 16s column. And lastly, I have all of the reset buttons, pins, tied to this button here so that as I'm simulating, I can reset back to 0 again at any point in the sequence. Now, through the magic of editing, I've turned this mod 16 counter into a decade counter. The decade counter will count up to 10, up to 9 before it'll reset. And this is useful for 7-segment displays. I can't display a 10 on a 7-segment display. I can only display a 9. So if my input goes up beyond 9 counts, I need to pass that information on to the next 7-segment display that represents the decimal tens column. So what I've done here is I've taken a NAND gate and I've tied one input to the NAND gate into my 8s column, and I've tied the other input to the NAND gate to my 2s column. So if this were to display a 10, I would have a high signal here and a high signal here, which would come through the NAND gate and convert to a low signal, which would reset all of my reset buttons back to 0 again. So all of those pulses that were stored in my flip-flops get wiped out, and it goes back to counting from 0 again. Let's simulate it so you can see it in action here. And he gets up to 9, and then now it's back to 0.